nanohub.org.
Online simulation and more for nanotechnology.
So today's the third lecture on generalized linear models. I'm going to say a few more things about Bayesian linear regression. I'll show you a little bit of the graph notation, which you can use to represent relationships between random variables, and in particular causal relationships between random variables, and it's extremely useful. Originally, I wasn't planning on doing that, but I thought I had a little bit of time, so I added it in there. You see what I mean later on. And then we'll talk about the evidence approximation. And the evidence approximation allows us to pick hyperparameters of our models, like, for example, the width of the radial basis functions or any other parameter that is not a weight. We can use the evidence approximation to find it. Or the regularization parameters of our priors, we can pick them with the evidence approximation. And I will also talk briefly about the automatic relevance determination method, which is a special prior that you can put in your weights that has the characteristic that it's going to kill most of the basis functions that are not needed. It's a special prior. You train the model with the evidence approximation. You see how this is done. And at the end of the day, if you have used too many basis functions, it's going to tell you, you know what? You don't really need this, and that. Okay, so the automatic relevance determination will allow us to kill a few of the basis functions and prune our model down. All right, so let me remind you again what our regression model looks like. We had a generalized linear model, all right? So that's ingredient number 1. And then we model the measurement process with the likelihood. And we're basically saying that the mean of what we measure is our model. And then our measurement is contaminated with our measurements are contaminated with some Gaussian noise. Okay, that's our key assumption. So as soon as we have the measurement model in place, the likelihood, then we also need to say something about all the other parameters that we have in our model, including the weights. Now, that something should be as vague as possible. If you know nothing, you should really pick a flat prior, and that's pretty much it, okay? So even though you are forced to say something, that thing that you say can be very, very vague, and it should be very vague. Anyway, and this is how Bayesian linear regression looks like. Now, a very common choice for the prior of the weights is this distribution, which is Gaussian. So you're basically saying, before I see any data, I think that it is equally likely to have positive and negative weights. And they're going to be distributed around 0 with this precision alpha there, which is basically an inverse variance. So the smaller this precision, the more you don't know about the weights, let's say. Okay, so if you pick a very, very small alpha, like 10 to the minus 6, you're basically saying, I don't know what the weights are, but I think they are less than 2 million and greater than minus 2 million. Okay, so this is pretty much what you say, which is a reasonable assumption if you have scaled your data properly. So even though this is a very specific choice, by making this alpha very, very, very small, it is actually can be a very, very vague choice, okay? Anyway, and then you put everything together and remember that all you need in order to update your state of knowledge about the weights is Bayes' rule. So you ask this question, you say, what do I know about the weights given all the data that I have seen? That's all you say, okay? And then you use Bayes' rule, and that becomes the likelihood of observing this data set given that your model is correct and given that you know the weights times the prior of the weights divided by a normalization constant. Okay, and you need to remember how to interpret this, of course. Prior state of knowledge, it interacts with the likelihood to give you your updated state of knowledge or posterior state of knowledge or your state of knowledge after observing the data. And this thing right here is just a normalization constant, which you can ignore for the time being. You can just say that this is proportional to that, but it's going to be useful later on when we talk about model selection. So it will turn out that this will give you the probability that your model is right, something proportional to that. But we'll look at that much later. And the way you interpret this is as follows. Again, let me say it once more. Why should I think about the weights after I see the data? This is how you interpret it. Okay, this doesn't mean that the weights are random or anything like that. You just don't know what they are. Okay? And the more data you see, the sharper this distribution will become. Anyway, of course, characterizing this distribution, it's not very easy, and the easiest thing to do would be to just pick the weight parameters by trying to maximize the posterior, just like you picked parameters by maximizing the likelihood. This is really bad. Don't do it. Especially for a linear model, you can actually do much more than just maximizing the posterior. So if everything is, if the model is linear, the likelihood is linear, is Gaussian, and the prior is Gaussian, then you can actually work out exactly this distribution. This distribution is going to be Gaussian. This is going to be homework problem number 1. Okay? So, and in this homework problem, you basically have to show that this is a Gaussian, and it is this Gaussian. A Gaussian with a mean that's given by this expression and a covariance that's given by that expression. Okay, you're gonna have to do that. Let me just tell you a little bit about it and how you are supposed to do it. It will take, I don't know, about half an afternoon. But it's not really, if you do it the first time. The second time you do it, it's a little bit faster. All right, but here's how you're going to do it. So first of all, you need to read Bishop chapter 3 because the solution is in there. Okay? So there are a few steps missing that you're going to have to complete, but it is in there. Okay? But anyway, here's how it goes. You're basically taking the likelihood and you're multiplying it with the prior. So let's take, this is equivalent to taking, let's say, the log of the likelihood W. What else do I have? I have a sigma, and adding to it the log of the prior of the weights, right? So instead of working with a probability, you can, where you multiply stuff, you can work with a log where you add stuff. It's a little bit easier, okay? Actually, you know what? I think that is not what Bishop does. So let's not do it this way. Let's just multiply things. Sorry about that. W sigma times PW. So you start with whatever is on the top, okay? And you just substitute for these expressions. So here are the substitutions. This guy right here is a normal distribution, multivariate normal distribution. So it is the PDF of a multivariate normal distribution evaluated at this vector. And what is the mean of that multivariate distribution? Well, the mean is your design matrix times the weights, okay? And this design matrix is, I remind you, are n rows, n is as big as the number of observations you have cross m, and basically the ij element of this matrix is your jth basis function evaluated at your ith observation, and the variance of that distribution is sigma square I, and you multiply that with another Gaussian distribution of Gaussian PDF, the PDF of a zero mean Gaussian with a diagonal covariance matrix. That's it, okay? So you look these things up, and if you look them up, I mean, I will give you the expressions and you're gonna have to do it again. You should get something like this. 2 pi minus 1 2n determinant of sigma square I times exponential minus 1/2 phi w minus y 1n transpose sigma square I inverse phi w minus y 1n. I'm going to post this anyway, times, so this thing is that. Of course, this you can find it on Wikipedia. And then the other thing is 2 pi minus 1 to m, where m is the number of base functions. And here you have a minus 1, I, there's 1/2 here, 1/2, exp minus 1/2 w norm 2 squared with an alpha here. Okay? Anyway, so this is how it looks like, and then what you do is you take this exponential and that exponential and you turn them into one exponential, and you take whatever is inside and you try to create another Gaussian. Okay? This is called completing the square. So you will go on taking this thing and that thing, putting them together, right, into a single exponential, and then you try to rearrange these terms so that you see this, whatever is in the exponential of that Gaussian. It is a little bit easier after you read chapter 3 of Bishop, alright? So the single reason I want you to do this homework is so that you demystify a little bit the process, and you gain a little bit of experience with the math. Of course, you should not really do it if you're writing a paper, okay? But I really want you to go through this to see that it's not really a big deal, it's just a little bit painful, okay? That's all. But it's completely doable by everyone, alright? So you do it once, you remember how you do it, but you're going to forget all the details, okay? And just because it is on chapter 3 of Bishop, this is going to force you to actually read that chapter, okay? So I really want you to do. So, yeah, good luck. Reserve half an afternoon just for that, please. More like a day? I think, okay, yes. If you're doing other things on that day too, yes. Anyway, any questions about that? All right, that's good. Let's move on. So we talked about the posterior of the weight that is going to be Gaussian, and you guys are going to have to derive it. But another thing that you're going to have to derive is also this thing, which is the predictive distribution. So now you have found the posterior of the weight, and you ask yourself the question, if I want to predict the response, or if I want to predict what I'm going to measure at a new point, x, how do I do that? Okay? And you ask yourself this question right here, which is, what do I believe about y if I measure at x after I have seen all the data? So this is what is here, right? So whatever is on the right of the vertical line is what you're conditioned on. So you're saying, what do I think y is at x, having observed all that data? Okay, so this is the right question to ask, and this is always the starting point. And the trick here is to use the sum rule to introduce all the quantities that you already are familiar with, quantities that you have already calculated. So if you use the sum rule, you can introduce this guy right here, which is basically your likelihood, your Gaussian likelihood. Okay, this is your Gaussian likelihood. And it's basically saying, well, if I knew exactly what the weights are, I can tell you what y is going to be. Okay, that's what it's saying. But I don't really know what the weights are. That's the best thing I can say about the weights, is my posterior about the weights. All right, so you say, here's what the best thing I could say if I knew the weights, but since I don't know the weights, I'm going to average over them. Okay, now this is really the sum rule. So you're going to have to show that this is the sum rule, and again, this should be on chapter 3 of Bishop, the discussion about how you get this expression, and you're going to have to actually do the integral and show that if this is Gaussian and that is Gaussian, then the whole thing is a Gaussian, and it is this Gaussian with a mean that's given by this expression. It's basically your basis functions evaluated, your basis functions dotted with the median, the mean of the posterior of the weights, and then the variance turns out to be that. Okay, so this is like your predictive mean, and this is your uncertainty. Okay, so you're gonna have to show this as well. And again, don't worry too much about it, because it is in this, literally the solution should be in the chapter, right? Isn't it? Okay. There are some steps missing that you should be able to figure out by Googling, I guess. Because it's really, I don't want you to do the algebra, right? Because it's just doing this integral, right? I don't really care if you know how to do that integral, but you can just use Wolfram Alpha to find it, or you can just Google for identities of Gaussian integrals and find an expression that matches whatever you get there, and arrive to this point. All right. So what is important for me is for you to understand what this means and why it is connected to this expression. Okay. So this is what you need to meditate on. Anyway, and then at the end of the day, we saw that the predictive variance consists of two parts. The noise part, which is purely aleatory and you cannot really reduce it, and this part, which is epistemic, and it is induced by the limited amount of data that you have. And actually, the more data you have, the smaller this is going to be, to the point where it's going to be eliminated. All right, and this is a visualization of these things. And again, you're going to have to visualize epistemic and aleatory uncertainty in specific examples. And for that, you should be based on the handout. Okay, another idea that we're going to explore in the homework is sampling plausible models. So the epistemic uncertainty, as soon as you have stopped collecting data, is going to be there. And sometimes you want to visualize it and you want to sample models that are compatible with the data and correspond to this kind of uncertainty. And basically the way you do it is by, for generalized linear models, you sample weights from the posterior of the weights, you plug them into your model, and then you visualize that, and then you sample another set of weights, and you visualize that as well, and you put everything together, and you start seeing things like that. Red lines that give you models, each one of which is as good as any other model, and you cannot really pick between them just by probability theory. You need something else to pick. But any of these models is good enough, is as good as the other, and you could of course sample 20 such models, or even more than that, like 100 here. And we're going to see a specific example in the homework where I'm going to give you the stress strain measurements for a molecular dynamics experiment. So we're going to take a crystal, and we're going to start applying tensile forces to it. And on each different step, we're going to basically measure how much it has deformed and measure the axial stress. And you're gonna see, because this data comes from molecular dynamics, there's gonna be a lot of noise. Okay, so the stress-strain relation is not gonna be a smooth curve, but it's gonna be a noisy curve. And your goal will be to take this curve, get rid of the molecular dynamics noise, and come up with a model for the stress-strain curve. Okay, the mechanical engineer should know what I'm talking about. Everybody else, you will see. Okay, I have included all the right Wikipedia references. So anyway, but the bottom line is that you're not going to be able to tell exactly what the stress-strain curve will look like from this set of molecular dynamic simulations. So you're going to have to quantify your epistemic uncertainty about it. And so you will see, for example, how this way of thinking can help you get epistemic error bars for things like the Young modulus or the yield stress. You will see all that. All right, and basically the homework is where you're gonna learn. Okay, so take it seriously. It takes an awful amount, a lot of time to put it together. All right, I hope it takes even more time to actually do it. So I'm sure about it, actually. All right, so let's see. But anyway, so this is what we saw last time, and this is what you should expect in the homework. And now there's these problems that remain. How many base functions should we use? Which base functions should we use? And how do we pick the parameters that we have introduced, like the precision of the weight, the noise variance, or other parameters? And this is what we're going to address today. But before I do that, I want to talk a little bit about graphs and how graphs can help you visualize some of these models, and how you can use graphs basically to... What can you do with graphs? So what you can do with graphs is avoid remembering anything that has to do with equations. So you can do everything with graphs. So I hope I can demonstrate that today with 2 or 3 slides, but if I can't, just know that I'm bringing up graphs from now on every single lecture, and I will show you how our models correspond to graphs. By the way, here is a very simple graph showing the relationship between 3 random variables, A, B, and C. And you can actually think of this as a graph depicting the causal relationships between the 3 variables. So A causes B and C. This is how you should think about it, right? Or B is caused by A, or C is caused by A. You can think about it like that, okay? Now, what I'm gonna say is the following. Each one of these directed graphs corresponds uniquely to a set of conditional independence relationships between these random variables. And I will show you what I mean by that, by example. Alright, so just by looking at that graph, okay, you see that A and B are not independent, right? Basically, B depends on A, obviously. There is an arrow going from A to B. Similarly, A and C, they are not independent. C depends on A, okay? And at the same time, B and C on their own, they are not independent. Okay, because they have a common factor. But what you can say is that B and C are conditionally independent if you have observed A. If you observe A, then B and C are independent. Here's now how you can use this idea to write down the joint distribution corresponding to this set of random variables. So I'm going to write down now the probability of A, B, C. The probability that A random variable A takes a specific value, random variable B takes a specific value, and random variable C takes a specific value. So I'm going to do that by looking at the graph, okay? And I will start by the end nodes of the graph, by the leaves of the graph. So I will start from B and C. And I'm going to write down the probability of B. Well, I cannot just write the probability of B. I need something to talk about B. And what I need to talk about B is all the parents of B. All the causes of B is what I need in order to talk about B. So I need to write it like that. Probability of B given A. I'm only allowed to write it down like that. Okay, because I need A to talk about B. That's what the arrow means. Alright, so I can write probability of B given A. Similarly for C, if you want to talk about C, you better tell me first what A is. Okay, so now we're done with B and C, and the only thing that remains is A, and A does not have any parent, so it just goes like that. Okay? So, the joint distribution of these random variables was decomposed into two conditional distributions, which basically explicitly encode the arrows, right? You see, so this is the arrow going from A to B, this is the arrow going from A to C, and there is no arrow going into A, so A is just on its own there. Okay? There's really only one way to understand that, and that is by doing a lot of examples. So let's just do this example. So now this is another model, again with 3 random variables, but now A and B together, they cause C. Okay, so A has no cause, it just happens. B has no cause, it just happens. And then A and B, they combine together to cause C. So now I'm going to write down the joint distribution for this graph. Again, I have probability of A, B, and C. Yes?
So in this graph, does it mean that for C to happen, A and B both have to happen, or either of them?
Yeah, they both have to happen. So this means is interpreted as follows. C depends on whatever values A and B have. Okay? Or if you want to interpret it causally, A and B happen before C. And they kind of cause C.
So it means that if only B happens, then C cannot happen.
Yeah. But this is about random variables, right? So I'm asking questions about random variables. Anyway, so how do we decompose that? We're going to start again from the leaves, from C, right? And we're going to start writing probability of C. And then we're going to put on the right of the vertical line all the parents of C. Okay, so we're going to put A and B. Because in order to talk about C, we need to know A and B. And then we go to the other nodes, and we see that A doesn't have a parent, and B doesn't have a parent. So it goes like that. Make sense? We're going to do it on every lecture, every model I introduce, I'll do this. Yes?
The difference between A comma B and A and B?
This is A and B.
And
And B, yes. Yes. This is interpreted as and B. So in order to say something about C, you need to know the values of A and B. Alright, so this, you read it as follows. The probability of A getting a specific value, B getting a specific value, C getting a specific value can be decomposed as the probability of C getting a specific value given that you know the values of A and B times the probability that A gets a specific value times the probability that B gets a specific value. And this we read it from the graph. Alright. Let's take a graph that's a little bit more complicated. Alright, so now we have 1, 2, 3, 4, 5, 6, 7 random variables, A, B, C, D, E, F, G. A causes B, B causes D. For E, you need both B and C. For F, you need E and C. And for G, you need F. Yes?
Well, how can we do if it's a two-way relation, like a chemical reaction AB becomes A plus? If it's a chemical reaction, if a composite of AB will becomes A plus B, how to deal with a two-way direction?
It doesn't work. Okay, so you need to use time to introduce more random variables. So you can say concentration at this time, concentration at a later time step, and this is going to break the two-way relation between. So everything that I'm talking about right now is for graphs that do not have circles. Okay? There should not be any circles in the graphs. So you cannot have D causing A. Then it's not a causal model. It's something more complicated. Okay? Anyway, so let's start at the leaves. What I'm going to do is I'm going to write down the joint probability density of this, all the variables together. A, B, C, D, E, F, G. All of them. Okay? So how do I do that? I start from the leaves. So let's start from D. So I can write probability of D given B. Okay, I'm done with D. I have to keep track of them. Let me then do G, probability of G. I need F for G. I'm now done with G. Now I can do perhaps F, probability of F. F needs E and C. I'm done now with F. Now let me do E times probability of E needs C, B and C. Okay, so I'm done with E. Now I can just do C now. C doesn't have any parents. It's probability of C, like that. Now I'm done with C. Now I can do B. The probability of B given A. I'm done with B. And I only have A that doesn't have any parents. And I get the probability of A. Okay. So it kind of looks obvious. It is obvious. All right. The only take-home message is that this is very simple to visualize for your models, but it is equivalent to statements like that. And it is usually much harder. I mean, you can just, so far we have been creating our models with such statements, okay? Explicitly just writing down these statements. But it is more difficult to remember these statements than it is to remember the graph. Or to just derive the graph from scratch. It is, you just think about it and you can come up with your graph. And as soon as you have the graph, you can get again these statements. So let me show you one more thing that you can use. Yes?
From the motorcycle example with the G,
Mm-hmm.
the graph ways, is it fair to think about that as just a very long chain at every single time step to have one of these models? Like A, B, C, D at every time step? Like the one group depends on the step.
Yeah, we could do it like that, but this is not the model we created. We created actually a model that is simpler than that. This will be a dynamical model that you can actually visualize just like that. And we'll look at these models on lecture 20. But we have a much simpler model. So let me show you this final thing about graphs, and then I'll show you how you can think of the graph, how you can make the graph of Bayesian linear regression. So here we have this graph, but now we are observing random variables D and F. Okay? So let's say whenever I say them, that means that I have observed them. Okay? So I'm observing D and F. And now what I want to get is the distribution of everything else conditional on D and F. Okay? Here's how easy this is. First of all, you write down what you want to get, right? So you want the probability of A, of B, of C, of E, of G, right? This is everything that is not shaded, condition on D and F. Just to clarify that, these are the things that you have seen, okay? So what is this probability? How do you get it? Where by Bayes' rule, to get this probability, you need the joint probability of this and that, okay? So you need the probability of A, of B, of C, of D, of E, of F, of G. Of course, you have observed D and F, that is fine, okay? But you need the probability of the joint. And just show you how you can get the probability of the joint from the graph, okay? And you need to divide by the probability of D and F together. Okay? This is Bayes' rule. Probability of A conditional B is probability of A and B divided by the probability of B. Okay? Any questions so far? So how now can you express this probability here in terms of this guy? You're going to use the sum rule to express this one. So now you can say, oh, you want this probability? Here's how you can get it. You can start with a joint A, B, C, D, E, F, G. Okay, here's the joint. Here's what you have observed, D and F. It's right there. And you need to average over everything else. So you average over A, you average over B, you average over C, E, and G. Does that make sense? Or if you like, the conditional probability that you wanted is basically proportional to the joint distribution of the graph, but wherever you have observed something, you just replace the random variables with their values. It's proportional to that, and then the what you have on the denominator is just the normalization constant. It's just something so that whenever you sum over everything, you get one. Some constant that has this property. That's all it is. Make sense? Anyway, we're going to practice with that, and you will see that if you think in terms of of graphs, it is actually very, very easy to get these complicated relationships. Questions? Okay, this doesn't mean that nobody understood anything, but I will come back to it. Okay? So here's now something about the model we created. Okay? So we said that if you observe x1, so at x1 we have a measurement y1. Okay, so I'm gonna look at each one of my measurements is basically a random variable. All right? And we have a model that connects x1 to y1. This is the model we have. Our generalized linear model is a model that takes an x and gives us a y. If we give it an x1, it's going to give us a y1. But in order to say what y1 is, it also needs w, right? It needs w. So we better add one more node. So I'm going to add it here, which I'm going to call w. So you need w to tell me what y1 is, right? Because the mean of y is basically the generalized linear model that requires these weights. But we have also said that the measurement of y has some noise, some Gaussian noise. And to describe that Gaussian noise, we need another random variable, which we call sigma. So we also needed that sigma. So this is pretty much the complete picture of our model, right? So at x1, In order to get y1, we needed w and we needed sigma, and that's pretty much all we needed, okay? And of course, we were observing both this and that. Right? We were observing these things. But we had also more measurements, and these measurements were independent, right? So we also had an x2 that gave us a y2, and we should have an arrow going like that. And these guys were also observed. And we should have an xn giving us a yn, and there should be an arrow from w going there and from sigma going there. And these guys were also observed. You see it? So this is the graph of our model. This is a graph representing Bayesian linear regression. Okay? And if you want, you can use the idea that we described before to write the joint distribution of all these variables. So you can say, what is the probability of let's just write w and sigma conditional on x1 to n, y1 to n. What is that probability? So it's going to be proportional. It's going to be proportional to the joint probability of everything. So we have proportional to the probability of x1n, y1n, w sigma, right? So this is a joint, and then you can start decomposing the joint by looking at the graph, right? So you start at the leaves and you come up with everything, right? So you say, well, I'm gonna start with the probability of y1 because y1 is a leaf node. So I have the probability of y1, condition on x1, condition on sigma, condition on w, dot, 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 probability of yn, xn, sigma, w, and then I need the probability of all the x's, and then I need the probability of sigma and the probability of w. Okay? And what have you observed? Well, you have observed all these things. This is it. Yeah.
Shouldn't there be a line from x to w and sigma?
No. Because x is just the input of, it's just an input to your experiment, right? So it's coming from somebody picking it. I mean, it could be you that picks x, right? Or it could be completely random.
Yeah. But with the example that you had, like time would be x,
Yes.
force would be y.
Time would be x.
The w varied with time.
No, W is fixed on the background. It specifies the model. So, yeah, X could be time, okay? Now the question is, why isn't there an arrow from X to W? Well, W does not depend on X. It's completely dependent. It just specifies your model, right? That's the only thing I can say. Now, of course, here you see that you have a probability of x, right, which will not play any role because you're actually observing x. So this is just a constant that it's not going to play any role. Yes?
For that to be equal sign, the probability of y1 conditional on x. No. The probability of y1
Condition on x1,
x1.
sigma w.
That looks like a 2.
Yeah, it kind of looks like a 2. That's true. 1. All right. So let me show you one simplification of this model. One simplification of the graph. So another way to do this graph, drawing fewer things. So this is known as the plate notation. So instead of writing this, you can do this. You can take a template of your model for an arbitrary measurement. So you can make it like that. Okay. And of course, you need your W and your sigma, and it's going to go like that. And then we make the convention that whenever we put a plate, this plate means that whatever is inside the plate is repeated depending on whatever index I put up here. Okay, so when I write that, this means that this plate is repeated n times. So basically it gets expanded to this. Okay, it's just a faster way of drawing it. Okay, and I'll show you now why the plate notation is, the graphical interpretation is extremely useful. So let's say that we want to extend our model a little bit. And let's say that we want to account for noise in the inputs. Right, so let's say that for the motorcycle data, you measure the time, but maybe, there's a little bit of uncertainty in that measurement as well. Let's say also Gaussian uncertainty. How would you do that? So let's create now a model with input uncertainty. You don't know how to train this model yet, but you can definitely draw it. So you have your xi, which is the x that you measure. Okay? But this is not the true x. Okay? The true x is, let's call it z. Zi. So it's like a true thing that you don't measure, but you measure x. Okay? So that true thing will influence your measurement of x through some noise, let's call it sigma x. Okay? So now you have a measurement process for your input variable. And even though you measure x, you don't really measure the hidden variable that gave rise to x. Does that make sense? But this hidden variable is what gives you the actual acceleration that you measure. Okay, this hidden variable uses this W to query your true model and then add some Gaussian noise to it. And this is a model now in which both the inputs and both the input and the output have uncertainty in their measurement.
What is Zi?
Zi is a hidden variable that you cannot measure accurately. When you try to measure it, instead of getting Zi exactly, you get, for example, a noisy version of Zi, which I call Xi, which could be, for example, Zi plus some Gaussian noise. Make sense? And it's always much simpler to draw the models like that. Draw the picture of what you really want to do and then start doing the probability. It's always easier to start from here. Yes?
In place of, if we, in that model, if we write yi, arrow from xi to yi, would it be wrong?
Yeah.
Go from x to y directly?
Yeah, without.
Yes, so the question is, what if I had an arrow that went directly from x to y? So here the assumption is that it is not x that causes y. It is a hidden factor that causes y, and your measurement of the hidden factor is x. Does that make sense? So it's this z that causes y. And you try to measure that z, and you cannot get it right. You have to add, you are adding some noise to it. Okay? So you are not allowed to put.
Between the two figures, the left and the right one. Between the left, we can see that xi cos yi, but in the right one, it seems like zi cos both, but not xi cos yi. So
Yes,
what's the relation between the two figures?
that's exactly right. That's the relationship between the two figures. So so imagine that you are making measurements of X and Y in your experiment, okay? And we're always going, we say, well, what is the X? The X is the controls of your experiments, your input, all right? And most of the time we assume, well, my inputs are very precise. I know exactly what the input to my experiment is. I only have measurement noise. So this is what you're saying in the first model. In the second case, you say, you know what? Maybe I cannot really control my inputs of my experiment perfectly. And whenever I try to set it to X, and X is what I measure, it actually goes to Z. Does that make sense? So this is a different model, perhaps for the same data set, but this model includes more detail about what is going on, right? So if you make this relationship between Z and X deterministic, right? For example, I have zero noise I can control the inputs to my experiment perfectly. Then this model will be exactly the same as that model. Because it wouldn't matter that you have this arrow right here. Homework, guys. This is what is going to happen. Yes?
So when we have the arrow from xi to yi without the arrow from zi to yi, won't it mean the same thing because yi is dependent on xi and xi is dependent on zi, so yi is dependent on zi?
What mean the same thing with what?
So if we don't have the arrow from zi to yi, but we have the arrow from xi to yi.
Here?
Yeah.
Then it will be exactly that model.
But in that, xi was not dependent on zi, but here xi is dependent on zi.
Why can't we add zi to the top of xi in the left model?
Because zi is not something that you observe. I'm not sure if I understand the question.
On the left, xi and zi are basically the same.
Yes, it is the same. They have collapsed. This is what happens, right? And then you're saying, so this is the naive way of thinking about things, that you have absolutely accurate measurements of your inputs, okay? And then you say, well, maybe I have some error in that measurement. So you say, let me introduce a hidden variable that corresponds to my input, and let me call x the measurement of that variable. That's all that happens here. Yes?
So sigma x is the uncertainty in the measurement of x.
Yes.
Sigma is the uncertainty in the measurement of y and the model.
Yes. And the model discrepancy. Which is a very bad model for the model discrepancy because it assumes that the model discrepancy is Gaussian, which may not make sense. Anyway, okay, so let's get back. So this model, by the way, this model right here, what is my goal in this course? My goal in this course is to help you guys create such models for your research problems. Actually, this is the most important thing, is to actually think of, each individual variable and how they connect together. Getting this graph right, this is the most important thing. And then, once you have this graph, this is why I'm gonna bring this up repeatedly. The problem is, well, okay, now you know that you observe the blue things. How do you get the other stuff? Okay? So this is the inference problem. Now here, the inference problem is trivial, and that's what we have been talking about. Here, the inference problem is not trivial. We can still write down the posterior, but we cannot really analyze it. We cannot get an analytical form for it. So to analyze this, we need things like Markov chain Monte Carlo, variational inference, and these will be the advanced things that we're going to learn, like 10 lectures or so. Okay? But of course, these are completely useless if this is garbage. I hope I made this point. And I will try to make it again and again. Okay? just another comment about how research is done. Most people work with models like that just because things are nice and analytic. Okay, so most of the time we make discounts on what is actually going on in our problem. It's because we don't know these two keywords. And even if we do know them, it is not really easy to set it up unless you know the tricks. Okay, so we'll learn these tricks. So it's always, the best thing to do is always start by what your model really looks like and only simplify if it is absolutely impossible to do anything here, or if you can show that it doesn't really matter. Okay, so we'll see these things. Anyway, let me get to the next type of probabilistic regression, in which we now introduce one more thing. Remember that we had other parameters in addition to the weights. We had this sigma that gave us the noise. We had the precision in the prior of the weights. If we were using radial basis functions, this L controlled the width of the basis functions, of the radial basis functions. So all these parameters, I'm gonna call them all together theta. Okay, all these parameters together, I'm gonna call them theta. And these are called hyperparameters. This is the keyword that you need to remember. So the weights will be the parameters, and everything else will be a hyperparameter. And here's the Bayesian thing to do: model likelihood prior on the weight. But look at that now. I have explicitly denoted the dependence of the weights on these hyperparameters and the dependence of the likelihood on these hyperparameters. So you can explicitly see them here. Okay? And then what I'm doing, the other thing I'm doing is I'm putting a prior on these parameters. So now I'm going to say, well, this sigma, it has to be something positive. So let me give it a probability density on the positive real numbers. That alpha, that is the precision of the weights, it has to be something positive. So let me also give it a prior probability on the real numbers. And let's draw this model again. So we have xi. Xi is giving us yi. Yi requires w, but it also requires sigma. Okay? And now what we're gonna do, w. And now what we said is that w requires an a, right, an alpha. And if you want to use radial basis functions, you can say that my radial basis functions also require an L. And all these guys here are your thetas. Of course, you have a nice plate notation like that, and you are observing this, and you are observing that. Okay? You don't observe W. Oh, yes. Thank you. I'm gonna make theta, I'm gonna make a red circle. So that's theta. Everything except W is theta. Yes. All right. So here's what we do. Right? So we write down the posterior of the weights and theta together. We say, what do I think about W and theta after seeing all the data? And that's likelihood times prior. But again, you can just read it from the graph. Right? So you're asking, what is the probability of this and that condition on this data? It's proportional to the joint. And then if you use that trick that I introduced a couple of slides ago, you can decompose the joint and you will see this. Okay? And you don't have to remember anything. I mean, you have to remember something, but hopefully less. All right? Now, Later we'll see how you can actually sample from this using Markov chain Monte Carlo or more advanced techniques. But now what I'm gonna say is this is too complex. Characterizing this is too complex. I'm gonna make a simplification, and this is the simplification I'm gonna make. I'm asking the question, what is the probability of theta? Let me just find theta first. What's the probability of theta after I've seen all the data? And then you can use the sum rule to show that it's going to be proportional to this. So this is pretty much like saying, this is the posterior of theta condition on the weight, but I don't know the weight, so I need to average over the posterior of the weights. We'll make this a homework problem. How exactly? How many homework? Don't worry about it. We'll give you more time, okay? But it's important to get all the ideas. I'll show you how this can be derived, but it's not really, it's like one line. And then you say, okay, so this is the posterior of theta is going to be proportional to that. And you start making approximations. One of the approximations you're going to make is that, well, you know what, let's make it very, very, very flat. This is my prior on theta, right? What is theta? It's sigma, alpha, all these parameters. But I think that you should probably be a little bit conservative with your choices about the priors of sigma and theta, unless you know a lot, right? So you better pick very, very flat priors. So what is the flattest prior you can pick? 1. Okay? So you pick a prior that is 1, then this disappears from here. And then you get that the posterior of theta is proportional to this quantity right here, which is known as the marginal likelihood. And then you take a maximum posteriori estimate of theta. So you say, I'm just going to pick the theta that maximizes, that gives me the maximum posterior value. Okay, that's all. So this is called the evidence approximation. And it basically corresponds, it works when your prior for theta is very flat, and when your posterior for theta, which is this quantity right here, is very, very sharp. So if you have enough data, it is going to work quite well. And it is convenient because you just need to be able to do this integral over the weights, and if you can do this integral analytically, then you can maximize over theta using a simple optimization algorithm.
Is one a distribution?
Yes. It's a distribution that is just flat.
Yeah, but the integral of one.
It is a degenerate distribution. It's a distribution that you cannot normalize. That's okay. You can use such distributions. As soon as this integral exists, as soon as this exists, then you can use it. So this is an important point. You guys are making your life very, very difficult, because now this is going to be in the... No, I'm kidding. So this is an important point, right? So if for example, theta is takes values on the real line, then putting a distribution on the real line that is completely flat will not be integrable. But this is totally okay, because it is totally okay if this integral exists. If this integral exists, then it is okay, right? Well, we're not mathematicians. I mean, I am, but I'm trying. Okay, so let's explain it. Don't put a flat prior. Put a Gaussian prior with a precision that it's extremely small. So small that it is almost flat. Okay? That's it. And if in the limit of making this precision go to 0, everything still works, we're fine. Okay? And for these problems, we are fine. So we can show, for example, I'm obliged to answer it. All right? So let's say that we want to put a prior on sigma, okay? And we put a prior on sigma that is good, like we can give it an exponential with a rate parameter r. This is a good prior, okay? And then this becomes more and more uninformative as this r goes to 0, right? So you put this and you do everything with finite r, and then at the last expression you take r goes to 0, and it's going to work. And it's going to work for any kind of prior that is flat in the right way. But anyway, you should not worry too much about it, because if it doesn't work, it will be so obvious when you try to do the math, you will just break down. Okay? So you will start getting garbage, utter garbage. And yeah. Do we have any homework on degenerate priors? Let's add it in the next round. All right. Anyway, so if we do, if we use the radial basis functions with 20 terms, and we use this to select sigma and alpha, I mean, that's the sigma that we're going to find, that's the alpha we're going to find, and we start getting results that are a little bit less prone to overfitting. And that's pretty much it. So you get, you will get some experience with that through the hands-on exercise, which you will do on your own, apparently, and through the homework. All right, but I'll show you something else that remains. So we can still not say how many basis functions we should use and which basis functions we can use. And we haven't really said what we should do if our prior is not flat. Now, this is something that we're going to discuss much later because it requires these advanced inference techniques. But these two things, we can address them right now, okay, by putting a little bit more structure in our model. And this is the kind of structure we're going to put in our model. We're going to look at each one of the weights independently. And on each one of the weights, we're going to give a different precision. So this model will look like that. So you have your xi and your yi, just like before, and these are the things that you observe. Now your measurements of y are noisy. Okay, so here's your nice plate notation. But now we're going to expose the w's, right? So now I'm going to introduce the w's one by one. So here's here's wj, and I'm going to use plate notation. Right, I have m w's, one for its base function, and all these w's give me y. So I just opened up the box called w, and I'm looking inside it. And now instead of using a single precision for each one of the weights, I'm going to use a different precision for each one of the weights. Make sense? That's all. That's the only difference, okay? And now what I'm going to do is I'm going to use the evidence approximation to get an estimate of this and that. Okay? So I'm going to calculate the marginal likelihood, which integrates over the weights, and I'm going to take the maximum a posteriori estimate, basically, of sigma and the alphas. Now here's what is going to happen. If you look at wj, let's put 0 here. This alpha j controls its precision. The bigger the alpha corresponding to wj is, the more concentrated the prior of that w is. So for small alphas, the prior of W would look like that. And for very big alphas, the prior of W would look like that. So this is for alpha j much bigger than 1. This is for alpha j of the order of 1 or so. Okay? And what is going to happen is that the evidence approximation will automatically set these the values of the weights that, of the base functions that are not needed. It will set the corresponding alphas to very, very big numbers, effectively eliminating these base functions from the model. And all this happens automatically. So Bayesian inference, if you like, automatically knows how to get rid of things that it doesn't need. And let me show you how the predictions are going to look like for the case of radial basis functions with 20 terms. And this is on your handout how to do that exactly. So what happened is that it basically threw away a lot of the base functions that it didn't need. Out of the 20 base functions, probably threw away about 15 or so. And the result of that was that we got basically much smoother fits here and there and here. The epistemic uncertainty went down significantly. So we just have noise uncertainty. And this is pretty much it. Yeah. So basically it said, you know what it said? I remind you that the basis functions, these basis functions, the radial basis functions, they look like that. Right? So they are bells centered at 20 equidistant points along the x-line. So it said, these bells, I don't need them because I can see that the response is 0. Throw them away. I'm going to keep the bells here. I'm going to keep the bells here. And these bells, throw them away. The response is constant there. This is what it said. Right? So this idea, you will use it in your homework to find the right basis functions for the stress-strain curve. Yes, that's pretty much it. All right, so for example, what can you do with that? You can apply this idea to any combinations of base functions. So now you can take your generalized linear model with polynomials, add to it radial base functions, add to it Fourier base functions, steps, whatever you want, add everything together like 100 different base functions, and then let these pick the best. Okay, that's what you can do. Question? Yeah.
Can you apply this to like discrete choice models?
Discrete choice models like?
So you have a bunch of inputs and the outputs are like discrete.
For classification models? Yeah, you can do that also in classification. So this the idea of automatic relevance determination is basically based here. So you go to the weights of your model and you put a prior that allows your model to completely eliminate this particular basis function. This is the idea. So you give your model the flexibility to say, I may not need that. If you give it this flexibility and there is enough data and inference is done the right way, it will automatically do it because model pruning is already built into Bayesian inference. You don't have to enforce it. You don't have to force it. You just have to give it the ability to do it, right? So if you don't allow it to, if you tell it there is a single precision for all weights, it will find a compromise. But if you give it the ability to pick a different precision, it will automatically throw away everything that it doesn't need. All right, guys. Thank you.